Okay, so here's our last video of the unit on transformers, and they don't really actually look like this. They actually look like this, and they don't. And we, like I say, we're not watching the movie as well. That can be your homework. But this is what a transformer looks like. So you've seen them all the time. The green box is nothing but a transformer. And you think about some things that you notice. I don't know if you've ever sat on the green box, but maybe that can be another bit of homework, is to sit on the green box. And you should notice they're a little bit warm, and you can kind of feel a little hum in them, and that's part of a transformer. And hopefully you decide to build a transformer as your lab in this unit, because it's a good one, and and you can get the feel of the hum. You won't notice the heat. The heat is just a little bit of lost energy to resistance, but that's it's not that big. So the question of why we use transformers, there's lots of reasons. The main one is transportation of electricity. There are others. Every time you see, and I'll show you in class, but if you have a plug-in and it's like a little box, the plug-in is actually a little box, that's a transformer. That means that whatever appliance you're using or plugging in, it doesn't want to use the same power, well, it wants to use the same power, but it doesn't want to use the same volts and current as comes out of the wall. And a transformer will adjust that, so your appliance has exactly what you want, what it wants. But the main reason why transformers were invented or designed was to reduce the amount of energy lost when we transport electricity from a power plant to wherever you're using the power. So I have an example here, and you don't really need to regenerate this math for me. I just want you to understand it. If you imagine, in our homes we use 120 volts out of our wall. Okay, now say the power plant made, and who knows what the power plant, what they make their electricity, what the voltage comes out at. But say they made it at 120 volts. So what got generated at the electricity generator was 120 volts and whatever amps that would be, right? And you wanted to send a certain amount of, and we send the power in watts at 120 volts. And there's a nominal amount of resistance in every single electrical wire. Obviously, and we talked about during the resistance part of the unit, how you can reduce that by having a thicker wire, obviously longer wires, but we know they're going to be long wires because they're coming all the way from Bruce, right? So we can't control the length. And then you can also choose materials like copper, for example, which has a very low resistance. And then there's also a ton of research being done, because there's a huge amount of money that can be saved by having what we call superconducting wires. The lower the resistance, it's just lost energy, right? It's just a total waste of energy. But a one ohm wire is about right, about what we might expect. So if we were going to figure out the current through our wire, and we knew we're making 10,000 watts at 120 volts, well, that would work out to about 83 amps of electrical current, which is a really high current, very deadly as well. But if we wanted to figure out how much lost power there was due to that 1 ohm resistance, it would work out to, of our 10,000 watts that we're sending, we'd lose almost 7,000 watts to just resistance in the electrical wire, which is clearly not acceptable, right? We can't afford that. So high current means high power loss to resistance. So we want to run our power lines at a low current. That's the goal. And so if, for example, we could set it at, instead of 83 watts, say we took a factor of, divided that 83 by 1,000 and used 0.83 watts, then your power loss resistance would be only not even a watt, which means almost nothing, right? Almost, it's an insignificant loss. So that's why, that's the main reason we use transformers, though they are all over the place. Just look around at all your devices. Every time you see your laptop, whatever, every time you see that little box on your cord, that's a transformer as well. So the problem is, of course, if we're running at 0.83 amps and we have 10,000 watts, that means we're running at hugely high voltage. And you've probably heard that before, right? You see the signs, high voltage power lines, right? Well, that's what it is. We run at high volts so that we can send the same amount of power with a low amperage, a low current. Okay? So in order to transport electricity, we need to increase volts. and that's what happens in the transformer. So this is a schematic of a transformer. So this is what's inside the green box, or inside your little boxes plugged into the wall. And what happens in a transformer, and again, the one you build will look just like this, and I'll show you a model of it in class as well. You've got this thing called an iron core, or I don't know if it's iron, but a magnetic core. Okay, a core that will transport a magnetic field. Okay, it's got a core in the middle, and then you've got two coils, and these coils they're not touching each other. They're not electrically connected at all. They're completely separate bodies. And what happens is if the primary side is the input, so what's coming in. So what happens is you send a current into the primary side. That current, based on Oersted's principle, will create a magnetic field. That magnetic field will be carried by the core over to this coil, and then in this coil, that magnetic field will create and generate an electric current based on Faraday's principle. And now you have while these aren't touching each other, this electric current will generate electric current here. And you should have seen that in the last video, actually. But this is it. And so the thing is, if you notice on this picture, right, this has that's the number of wraps, right? So what is it, 6 wraps around the coil? And this one's got, I think it's 15, but it's got more. And so what that means is the number of wraps dictates the voltage, because the number of wraps will cause the electricity to slow down, so it'll decrease your current. And when it decreases your current, that means keeping the power constant, it'll increase the volts, and that's what happens. So if the number of turns on the primary coil is less than that on the secondary, which is the case here, then the volts is increased and the current is decreased, and the power is held constant. And you can think of it as being, well, that extra number of wraps is going to slow down the current. It slows down the current, therefore the volts will go up. And we call this specific type of transformer where you're increasing the voltage and the number of turns goes up. Turns is the number of wraps here, like this is 6 and this is 15. So this is called a step up. We're stepping up voltage. We're decreasing current, but we're stepping up voltage. So it has the title step up transformer. So in a step up transformer then, we increase volts and we decrease current. Now a step down transformer, on the other hand, is just the opposite. You can't see it's not a very good picture, but the number of wraps here, there's like 50 on this side, 10 on this side. And what I like this one though is we see like the number of watts doesn't change. The power itself isn't changing. We're not creating energy, we're not decreasing energy, we're keeping it constant. It's just the form of the energy changes. And in a step down, that means the number of wraps decreases, right? There's more wraps on the input side than on the output side. The number of volts decreases and the amps increases. So what you see here is, see it's 5 to 1, right? So the turns went down by a factor of 5, so did the volts, while the amps went up by a factor of 5. Where all this stayed the same. The power itself stayed the same. So in a step down transformer, the volts decreases and the amps increases and the power is constant. So when we transport electricity, then this is what happens. It's produced at the power plant at I don't know what volts, but lower than it's transported at. And then we use a step up transformer to increase volts and decrease amps. Excuse me. It's transported through the lines, and then when it gets to Stratford, it usually happens through a series. It's not just, it doesn't just get to the green box, right? You see usually when you can see in town, I think it's near Packham Road, where the main electricity comes into town, and there's a bunch of transformers there, right? That decrease from what it's sent at, right? It's decreased, and then usually as it comes closer to your home, it's continually sent through green boxes. You get through until it's decreased. So we could have it at 120 in our house, 120 in our wall. Okay. So here's a picture, like this piece here. This is what I was talking about, the little box. This thing's a little transformer. So whatever this plugs into doesn't want to use 120 volts, which comes out of our wall. It wants to use, so if this was the one for my laptop wants 16.5 volts. So my laptop uses 4.5 amps. So what happens is this little transformer steps down the voltage, and it steps up the current. And so these are very common. All kinds of appliances use that. There's a third reason that every home has a transformer sort of just at the interface between us and the power coming in from outside, right? So it sort of insulates our home from the rest of the grid. We're a bit insulated, and because if you remember looking at the design of a transformer, these, imagine this is coming in from the grid, from the neighborhood, right? And this is what we use in our home. There is a transformer that's neither step up nor step down, so it would be 50 to 50, so to speak, or whatever it is. But the idea is that because these aren't electrically connected, if you do something awful over here, right? You have some wicked short circuit of fire, it's not going to affect your neighbors because we're not actually electrically connected to our neighbors. So those would be 3 reasons to use transformers. Okay. So just some terminology as far as looking at design of transformers, or just pretty much the equations related to transformers. When I say IP, that means the current coming in, the primary. IS is coming out. Same with voltage. And this is N, is what is the symbol we give for the number of wraps on the coil. So here's the equations. And normally anything I give you in this class especially, you can avoid the use of the equations. You can use them if you like them, and I'll show you how to, but usually you can just use your logic to figure things out, and I'll show you what I mean by the examples. But the idea is that the language used is proportional. So number of turns is directly proportional to voltage, means that if I increase the number of turns, the volts will go up by the exact same factor over the course of the transformer. And that was the idea of, if I went from 10 wraps to 50 wraps, that means my volts would go, say, from 100 to 500. It follows the exact same. Its input voltage and current go in the exact opposite direction, right? And that's because that's to keep the power constant. So as volts go up, power goes down, current goes down, and then current is indirectly proportional to the number of wraps. So if the number of wraps goes up, the current goes down. But we'll see that through the examples. So here we have a step-down transformer. The input voltage is 120. The windings, or the number of wraps, the primary coil has a 250 and has 25 on the secondary. So calculate the voltage. So it comes in at 120, and then we don't know what it comes out at, but we do know the ratio of the number of wraps, and that's sometimes called the turn ratio for the transformer. So the turn ratio is 250 to 25, or you could just say it's 10 to 1, right? Because it goes down by a factor of 10. And that basically will tell you the voltage. The voltage will follow the turn ratio. So here's the formula, if you wish to use it, or you can just say, because it's going to follow the turn ratio, so the windings goes down by a factor of 10, so will the volts. Okay, it goes to 12. Okay, example 2. We have a step-down transformer using an adapter for a cell phone charger. It has an input of 120, as they all do out of the wall, and out of it comes 5. So the current in the primary coil is 0.1 amps. That's what's coming out of the wall. And so what's the current going to the cell phone, right? What comes out of the adapter? So it's the exact same question. You can use the equation to solve this. I know you've got it in front of you. Or you could just say to yourself, okay, the volts is going down. What's that ratio? It's going down by a factor of 60, I think. So the current will go up by the exact same factor, not 60. Let's see. Oh. Yeah, here we go, 24, not 60 at all. That wasn't very good math. Okay, so the voltage is reduced by a factor of 24, so the current's got to go up by a factor of 24. So that number is not as easy to work with, but so the current was 0.1, so it's going to be 24 times it. If that's how much the voltage is reduced by. Here's the exact same thing, but using the formula. Okay. Okay. So this is an important thing. I always ask this on tests. Why is it that we use AC current and not DC current? Because I don't know if you've ever seen that, but on the walls, always it's coming out at AC. Why is it that we use AC? You'd think DC seems to make sense. You know, why would you have to have this fluctuating current all the time? The reason why we use AC current is because we need AC current to run our transformers. So all the transformers that we use couldn't function if you had DC current going into it. So if you tried to use a battery and plug it into your adapter, you couldn't do it, right? Because your adapter has a little transformer in it. You couldn't do it. You have to have the alternating current coming in, because the idea, the whole in the design of a transformer, you've got you know, you have to induce the current in that secondary coil, and to induce the current in that secondary coil, you have to have a fluctuating or moving magnetic field. That's Faraday's law. And because of that, if you don't have that fluctuating magnetic field, you're not going to induce the current, so your transformer will not function. So because we need transformers, there's no better way to do it. We use alternating current. We make sure that our generators at Bruce are alternating current, so they do not use a split ring, right? They're going to use just a regular ring, so the current alternates all the time, and we need the fluctuating current for our transformers to function. Put a circle around that. That's important. Okay, that's it. That's a long lesson on transformers. That's the last one for the unit, though.